Hello everyone, welcome back to our YouTube channel, Becoming a ROS Developer here at The Construct. My name is Rodrigo, and today we have one of our students, Justin, who has completed one of our courses, ROS Basics in 5 days. And at the end of this course, you can complete a project to get a certificate with us. And this project is actually implemented on a real robot. So that's what we will be seeing here today. So hello, Justin. How are you?
Good. Thanks for having me.
Thank you for coming. So yes, whenever you want, you can start sharing your screen and show us what you've done with your project.
Sure. Um, Sorry, yeah, I just minimized the Zoom window. Okay. Um,
All right, we can
so
see your screen now.
so first things first, I'll show the show the robot working correctly,
Mm.
uh, as intended. Oops. Okay. So starting out, should be looking for the uh nearest wall. Sorry about that. Um, And it's going to be giving me indications of where it's at in its wall finding status. So seeing an aligned true, so it means it's lined up to the wall.
Mm-hmm.
Then we get approach true. So it's approached the wall and got to the right distance. And then we turn and get the wall on the right side and we see a ready status. And then it tells me that it's in position. The wall is found. And then we say the service is complete and then move on and submit a goal for the odometry and start the wall following. So you see this goal accepted,
Uh-huh.
executing goal, and here we start recording total distance traveled. We've got a distance to start, and yeah,
What is
keeping it
that distance? Oh, like the distance that you have traveled from the start? Or
right,
why is there
right. So
two, total distance and distance to start?
so we have a distance to start. So at the very beginning, right when we start, or right once we finish the wall alignment,
Uh-huh.
we record a coordinate and um, then start tracking around the arena. Um, the distance to start is important here to identify when you've completed a lap. So when the
Oh, to
distance to
come back
start,
to it. Uh-huh.
right, right. So you'll notice the total distance and distance to start starts to deviate, and actually the
Yeah,
distance
I
to
see that.
start will actually start to come back down. Um,
So
right.
then the start of the wall following behavior, that depends on a successful return of the service.
That's correct. So I'll dive into that in a little bit and
Great.
show the process of how the code is working. But right now, just yeah, showing the proof that this works as intended, and then I
Yeah,
can
yeah.
show you how I did it.
It's
Um,
smooth. I don't see it sort of snaking through. That's interesting.
oh yeah, so I'm curious: is do you have a lot of them doing this kind of zigzag motion?
Well, it depends, right? Because we just provide an objective and it doesn't matter how it is reached, right? So the simplest is just a bunch of if else. Oh, there you go. We got someone in the office back there. But the simplest thing is just a bunch of if else, which means if I'm getting too far away from the wall, turn. If I'm getting too close, turn the other way. So that results in a snaky behavior. But of course, that looks really nice. So maybe I'm wondering if you have a little controller in there. What's running in there?
Yeah, yeah,
Yeah,
yeah, I do.
which is
So when
of
I
course
started out,
extra.
sorry, what was that?
I'm saying it's not part of the requirements of the course, but it's always really nice, and I'm always really curious to see how people have solved that issue.
Yeah, that okay. So there, return to the starting position.
Nice.
Um, Says robot has returned. One lap completed, stopping, and this is the total distance.
The total distance, yeah, which is 5.3. Well, yeah, which is a lot, not a lot more, but a lot less, I'm sorry, than when people do snaky, it's usually like 6 meters. So it's like almost 1 meter extra. And it's
Oh yeah, I didn't
interesting.
even think about that.
Yeah,
But
yeah.
yeah, you're right. There is a control in there. And when I started this course out
Mm-hmm.
and trying to learn everything, yeah, it was zigzagging, and I didn't
Ah.
really like that. Um,
So great. Well, now we see that the is perfect. So yeah, if you could just explain a little bit how you solved these sections.
how is that presenting? Not
I
correctly, I
can
don't think.
see. Yeah, I could see like right now. I can see like the PowerPoint window.
Okay. So this is my name. I'm Justin Kibbe. I'm gonna getting my master's in aerospace engineering at the University of Houston in Texas. My focus inside of this degree is fluid dynamics and robotics. Um, so just in case this wasn't clear, the objective here is locate the nearest wall, orient it with the wall on the right side, move the robot around the arena, um, and maintaining a specific distance, and then also track the total distance that the robot has moved. So some of the differences that I noticed, this first difference I noticed immediately in the first section, the wall following,
Mm-hmm.
was in the simulation. You set up your laser scan and you're pulling indexes from this laser scan message. And the minimum angle here is defined as 0 radians, which was directly in front of the robot, and then it rotates 2 pi around. And you have this angle increment, uh, which when you divide this total uh, 2 pi distance or yeah, radians around the robot, and you divide
Mm-hmm.
by the angle increment, you get 360 uh, entries for your message. So if you're looking for robot directly in front, that's uh, 0 on the array. If you're looking for directly behind you, that's 180 on the array, so on and so forth. And in the real robot, it doesn't start in front of you. It starts behind the robot at the 6 o'clock position and then does a full 2 pi radians scan. And the increment's also smaller. So instead of 360, you have 720 entries in this message array. Caused a lot of frustration initially, but using some of the troubleshooting from the um, practice, you can find out the information about these um, topic messages and get the right uh, entries. The next thing I noticed, or that I learned, which also took a lot of time and a lot of help from the forums, was the frequency in which the topics publish information. In the real robot, I mean, in the, oh no, I have these backwards. This is 600. And in the real robot at 1600 hertz. So in the simulation, I would get messages published to um, the command or CMD velocity, and I would get messages published from laser scan at a frequency of 600 hertz, and the robot or the simulated robot could handle that flow or bandwidth of information. So I didn't have any problems. But when I moved to the real robot, um, the frequency it published was 1600 hertz,
I'm sorry.
and
The
it did
frequency of publishing of what of the lidar
of the
or the
velocity
command, the
of
velocity
like what,
commands,
yeah, so if I was in a while loop, and within that while loop I was publishing velocities to,
velocities. Okay.
yeah, and so it was publishing at 1600 hertz, and so I've overloaded this bandwidth, and the robot is acting laggy. It's it'll tell me that it's aligned to the wall, but then it's still executing velocities and
In the
rotations
queue,
based
right?
on old information. I would go so far as just to eliminate the queue entirely, just one queue size.
Mm-hmm.
It didn't work. And with some help on the forum, we found out that, yeah, it's a really frequent publishing. And so if you put a timer into your callbacks, you can reduce this frequency and
Right.
reduce the bandwidth on your robot. Okay, so here's the control. Um, well, part of it. So the wall follower and how I solve this, defined a key laser indexes used for the wall distance, and also for tracking the robot angle. Here off to the right, I've tried to draw this up with a wall as this blue line,
Yeah.
robot as this circle, and then we have this right laser and front laser. And then if I do 15 degrees offset from the right laser, I can determine the angle that the robot is oriented to the wall. So using this angle, I can start to apply correction uh, factors to my angular velocities.
Hmm.
So in the wall follower, we call the wall finder service, or sorry, not in the wall follower, but in the main wall following program. Yeah, call a wall finder service, call the odometry action server, calculate a robot angle, which I just kind of explain, and use a correction factor to augment that so that I'm not zigzagging. And then also define the motion logic for uh, following around the arena to maintain the ideal distance and prevent wall collision.
Hmm.
Um, So yeah, within the wall finder, so when you're locating, trying to put the wall on the right side in the very beginning, I defined statuses to let me know where it's at in the code. So which I uh, pointed out at the very beginning, you have this aligned approach ready and then wall found. Um, so the first part is turn the robot until it's facing the nearest wall. So I do this by finding the minimum laser reading in the laser scan message and set that or rotate the robot until the front laser is roughly that same distance, and then publish the state aligned. Approach the wall until I get a desired distance, and then publish a state. So that would be approach, and then turn the robot until the wall is on the right side, which would be ready. And the same thing applies. I just turn the robot until the minimum laser reading is now roughly equivalent to the right laser reading instead of the front. And then publish the completion of the service, so it's done.
Mm.
Um, for the odometry action server, I'm extracting positions, saving the initial one, and then record and update the list, the odometry record list every second with a new coordinate. And then I calculate the distance between the last entry and the second to last entry, and I can figure out the distance between those 2 points, and then cumulatively add those distances, and I can track the total uh, distance like that. In the same way, I can calculate the distance to the start. So if I have that initial reading, I can compare that to the very last reading in the record list and track where I am at from the start. And so here you can see on this on the right, if the distance to the start is less than a certain amount, so it means I've gotten really close to the start, but also the length of that record is longer than 150, then I can say that the goal is compute and shut everything down.
Mm.
Um, Initially, I ran into issues where the distance to start would be low and it would shut down immediately because,
It
um,
completes the condition right away.
right, so I had to add this length in there. Um, so some of the things that I learned while doing this was that you can use a while loop to block out progression of code. So if you need to wait for something to finish, you can use a while loop block. I also ran into a problem where I wrote some methods, and it turns out that those method names were already predefined in ROS, and so uh, when I called those, I wasn't calling what I had written as a method. I was calling this inherent method uh, from ROS, and so
Like
from
which
then
one?
on, what's that?
Like what?
I think I had something like a publisher or publish or something like
Oh,
that.
and it was called, yeah, okay.
Yeah, and yeah, it would call a ROS function and not what I was trying to get it to do.
Uh,
So then I would go and create very unique names for my methods to make sure that there was no no overriding. Um, Using text loggers to track code progression. So a lot of times we'd use the loggers to debug. Um, I ran into a massive or this very frustrating problem where I couldn't get the add done callback for my action server to, or in my action client to trigger, or what I thought was not triggering. The very first line of my callback for
Action
for
server.
that method, yeah, for the action client was it had a logger, and then I wanted to print a variable uh, value. I had input that, or I'd written that variable value incorrectly, and so the program would just hang up there. I wouldn't get a
Mm,
logger, I wouldn't get any notification or error, and so I thought that I was never entering that callback, when the truth was I was entering that callback, but the program was just getting hung up on this incorrect uh, variable call.
right.
And
And
so if I,
I'm sorry. In this logger, is it was you mean just information printed out on the terminal?
right, right.
Oh,
So
okay.
yeah, within the call, and I would place, I thought by placing all these loggers in different spots, I could track where I was at in the code. But after this, I learned when I do loggers, I'm just doing a logger text like inside this callback or finish with this callback or exit while loop.
Right.
And if I wanted a variable value, I could do that in addition. But um, yeah, I would from after this lesson, I would just use text loggers, no variable calls inside the loggers.
Right. You could, I mean, you're mentioning this happened to you during your action. You could have put that in the feedback as well, right? So you have a feedback in your action server, right? That is, I think that's what it was printing out the distance traveled. Is that the action feedback, or is that like a logger that you added uh,
So um,
yourself?
yeah, that there's two. There's a logger inside of odom record,
Uh huh.
which is what I was using to try and troubleshoot.
Yeah.
But you'll see actually that the feedback is also being published. Um, so this this would be the logger.
Uh huh.
So ODOM action server, and this is the feedback from the service. This is the action client part.
Okay. Yeah, because you can. I mean, you can create a custom interface that will allow any feedback you'd like. And I was actually gonna mention this because you kind of in your service. You implemented these states, right? So you mentioned
Right.
you wanted to know where it was at, and basically what you were doing, kind of, is trying to convert a service into an action, right? Because you want to know what is happening in the meantime.
Oh,
Uh,
like that's my
so
feedback.
so that's what the feedback is, and then you can use that. So basically, the wall finder is better implemented, in my opinion, in an action server. But we have to show, all the three things you can do with ROS too. So in that case, you can add those states as feedback, right? Because so when you run, and then you don't block everything, so it's not like you're just waiting for the response. You can do other things, and like take action if the feedback goes incorrectly, something happens. So I thought it was really interesting that you were kind of inadvertently changing that service server into like what an action server would do for you. So now you know next time
Yeah.
to
Yeah, I didn't think
implement.
about that.
Yeah, yeah. For example, a service will do like a photo, taking a photo. When you don't really care about what's going in the middle, and it's really quick and simple. So
Right.
taking a picture or getting coordinates, something like that, you do a service. Um, Sorry, I interrupted you though. I thought it
No,
was
that's fine. That's
curious.
that's interesting. I hadn't thought about it like that, but you're absolutely right that those status are publishing there or is like the feedback.
Basically, the feedback. Yeah.
So that correction that you saw that so that to prevent the zigzagging, um, um, it's not so easy to see here, but what I'm doing is using these angles here.
Mm-hmm. Mm-hmm.
I'm calculating these angles here, angle with the wall, and then I create a correction factor based on that angle.
Oh, okay.
Um, the drawback here is that if I'm at an angle greater than 90 from the wall, then my correction factor is over 1. And so you'll see here these correction factors are multiplied by a certain angular speed.
Oh, because you
And
have
I
to.
don't
Uh-huh.
I don't want to go above a certain speed, so I also have a correction factor chop. So if I say if it's over 0.99, then just set it to so I can guarantee that I never go over this speed when turning. Because I know that there were speed limits within the real
Yeah,
robot.
yeah, those are mostly just to make sure nothing happens. But so
So
that this means then once you're approaching the wall, the angular speed varies and it slows down as it approaches the wall, right? Is that uh,
yeah,
correct?
so um,
Not
well,
as it
say that
approaches, as it rotates towards, because that correction factor is affecting the angular velocity you're sending to the robot.
right.
Um, Oh, but you're sending also a linear velocity. Oh, I see
Yeah,
what you're doing. Oh, that's awesome. So based on you have a constant, well, constant, kind of constant linear velocity, and based on that error that you're seeing as you move forward, you do these little tiny, and that's why we don't see them because they're tiny, right?
right,
They're
right.
okay. Oh, nice, nice, nice. That's a really nice way. I thought you were. I thought this was for finding the wall, but now I see that it's for the actual wall follower. Nice, nice, nice.
Right. So we've got a sweet spot of distance that's in between or less than zero point 0.3 meters and greater than 0.22 meters. I have a higher angular velocity and apply a or I have a lower angular velocity and apply a correction factor to it. And then if I'm outside the sweet spot, that angular velocity increases. So I have a stronger uh,
Mm-hmm. So
correction.
in here, I'm going to make another comment that maybe I'm wrong, and but I think in here you also kind of inadvertently sort of implemented like a simple PD controller because you are that correction factor can be you know taken as the error that you're uh, computing every time. You know that correction factor can relate to the error. Uh, so and that's why we also see this movement like this because it's going to be changing according to that correction factor. So there's a way to I don't know if you know if you've done this, but you can just get a simple PD controller method, and you just put the error that you want to minimize in there, and then the goal. So, for example, in this case, would be like the distance on the right side. I want it to be 10 centimeters, and the error needs to be I don't know 0.1, 0.01. So you input those, and that's kind of what it does inside. That's also nice to see. That you came up with your own way to sort of smooth this movement out. That's nice.
Yeah, thanks. Um, outside of that, um, oh, so this get result callbacks. This is when I shut everything down. This is that logger that I was talking about. I put 1 lap completed stopping robot, and then I had this variable called incorrectly, and it would get hung up right here. And so I would never progress into
Mm,
this callback. But because I was getting an error on this logger, it wouldn't print anything, and so I thought I was never entering into this, and I couldn't figure out why this add done callback right here was not executing. But
right.
yeah, so
Makes sense. All right. Is that it? Is that it for your
yeah,
presentation?
yeah, that's it. Unless you had some other questions you want to dive deeper into the code, I can talk
I
about it.
mean, I'm I pretty much covered every question. I interrupted you, so sorry about that. But I thought it was just
No,
a little more interactive but yeah, I mean, I just want to say congratulations. Really nice project. You know, did what you needed to do, and you know, you also kind of went a little bit further in these methods like that correction or the way you are turning the service into an action. Basically, I thought that was interesting. But other than that, no, I don't have any questions except you know congratulating you and yeah.
Thank you.
All right. All right. Well, actually, yeah, I do have a question.
Sure.
Uh, so, yes, you were using. You talked about, you know, the angles that you were using to make sure you're going straight, right? Like the
Right.
diagram you showed. Uh, do you think you could use this as a way of using these angles and the same kind of thinking to determine if what you're looking at is an obstacle or the wall?
Okay, so yeah, I did get into this. When I tried to do the wall finder, I wanted to implement this same process. And I did initially start out doing that and trying to determine what was an obstacle and what was a
Uh,
wall. Yeah.
you could do the
So
same that thing, but in the wall service, what I'm thinking right now is standard deviation, right? So
that's exactly what I used.
yeah, you see the top right, and then the your top reading and your bottom reading at that point, and then you see the standard deviation of all those points. If
So
it's little, it's probably a wall.
it's I think I took it out. But yeah, I had an average. So I would get, oh no, 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 it's still here. This is an unused variable, but it was used initially in the wall finder, and then I
Hmm.
scrapped this idea, but I would take the average of the three readings
Right, right.
um for my three lasers, and then I would find a standard deviation between them. And if one of the lasers was really far off from that standard deviation, then I would keep turning because I would say, well, then that's not a wall.
Hmm. Hmm. Yeah, and
Um,
I think it's interesting that it's the same principle almost that you can translate over here to create a simple filter.
right.
Awesome, awesome, great. Well, that's it for me, Justin. So congratulations. That's all the questions I got. So I just want to say
Thank you.
congratulations. All right, and to everyone else that is watching, just know that this is what you can do when you finish our courses and you want to showcase the learnings you've taken away from our ROS 2 Basics course. So I invite everyone else to do what Justin has done here and present your project, and you'll be able to get a certificate from us and take your learnings away from it. So thank you very, very much, Justin, and to everyone else that's watching. We'll see you guys for the next presentation. Bye-bye. All right, cool, Justin, we're done.